one, we have a byte. How big is the byte? 8 bits. I'm going to give you the unsigned so we go to the 8th, which is 0 to 255. So a byte are char, regular programming, are a bool. So this is what we use for bools, bytes, and chars. They're all 8 bits, and they go from 0 to 255. Right? The bool basically is 0 is false. Anything greater than 0 is true. So basically, we waste 7 bits basically to represent the true or false in a bool. The next is a short. You know how big the short is? 16. So we have 2 to the 16th. So we can go to 0 to 65,535. Okay. Pretty big number. Also, sometimes it's considered to be a word. So whenever I say word or short, they're the same thing. It's a 16-bit data type.
Is it always unsigned?
I'm just giving you the unsigned numbers. If I do, I could do some of these. If you signed, it's going to be negative 128 to 127. Right? And I'm not going to do the other. Basically, is minus by half, minus 1 to the positive side, put a negative side of negative. Basically, is why we get one more negative number is because we counted 0 as a positive number. So 0 is in the 127. So that's why I get 127. Next, we have int, which is 32 bits. So we get 2 to the 32nd power, and I'm just going to go 0 to 4 million, 4 trillion, sorry. Billion, 294 million, 967,295. The next one is a long.
Are we gonna have to memorize the?
I never tested on it.
It's a good idea.
But basically, I'd say it's for your knowledge. Basically, that way you know. One of those ones where if I only need to represent a number between 0 and 255, I don't want to use an int. It's a waste of bits. So this way, it allows us to represent different values. See, if I need the number greater than 4 billion, I need to use a long. because we only have, in the LC3 program language we're going to use, we only have 16 bits. So we only get to use 16 bits. Like I said, on your Intel architectures, we got in some long longs and stuff. We make a lot bigger numbers. That's mostly just because programmers have written programs to make these data types work on larger architectures. So float, long is 64 bits. 2 to the 64. I'm just gonna go really big, right? It's like 10 to the 19th power. It's like how big it is in decimal. So I didn't know if there's what the numbering system is on that. And then the last, we kind of call this a special one. Float is different than everything else, but it has 32 bits. And we have a double, which is 64. I'm going to briefly mention this at maybe not today, but float is very, I'd say, complicated, interesting. It doesn't follow the rest of these integer values. These are integer values, these are decimal values.
What's the difference between the long and the double?
So this basically is, I can do 0.3. These I can only use 64, or 4 million.
So long is like a bigger integer.
Yeah, really big integer.
They're all long.
This allows me to do
Fraction.
floating
Whereas
point.
double is like a larger float.
Yeah. I get a lot more precision, basically what I'm saying. I get a really small, I go like 0.00000002, really small decimal number. So, yeah. That's good. Here we got this down. I'm going to erase it again. Okay.
But for the double and long, before you said the long it was 10 to the 19th. Would double, does that mean that double has 19 spaces that it can write into?
Let me show you float, what it looks like, because it's not, you can't just convert. It's a mathematical formula they came up with float and double.
Okay.
So it's some really special math. I'm just gonna show you what each bit represents. I'm not even gonna do the math in class, because I even screw up all the time. I try and do the math, their formula. So I'm just gonna show you it for float and double, and then actually no, I'll skip to it now since you guys are asking about it. So basically, this is the only part I'm going to ever ask on the test, is what I'm going to show you here on floating point. Alright, so the float we had 32 bits. So we're going to draw this box. This is 31, 0. Alright, so this is a bit here. So if I go, the first bit here is our sign bit, just like normal, like we mostly do normally in others. Okay, after the sign bit, the next 8 is the exponent value. And then the last 23 is called the fraction. Okay. I know that's going to confuse a lot. Basically, this is all I want you to remember of floats. Right? Basically, is first bit is the sign, the next 8 is the exponent, and then the last 23 bits is called a fraction. So,
It's pretty much putting it into 0.000 time raised to the exponent.
yeah, kind of. So this is the formula they did. So my number equals -1 to the sign bit. So if I have, say, 0 to -1 power is -1. 1 is 1. So when 1 to the 1 power is -1. So you see how it worked? We times it by 1 point, the fraction. So whatever number this is goes into that part of the fraction. So it's going to be 1 point. If I had, I'm just going to go 1, so it's going to be 1.1. If I put binary 1 here, so it's going to be 1.1. And then we do times 2 to the exponent. Minus 127. Alright.
That gets us just the formula?
Yeah, so that's why I said to me, I screw up myself. That's why I don't even qualify. Basically, this is what they came up with, how to represent a floating point number using binary numbers. So they use these this formula. So when you print out a float on the screen, in binary it looks, you'll see the bits like this, and you have to go through this formula to output that floating point number on the screen.
Do that.
What? We're not gonna do that now. No. We're gonna let someone else handle that for us. But those who are interested, this is what it looks like in binary. See, all I'm gonna ask probably these questions here of what are the bits. So, any questions on that? I know it's confusing. It's confusing for me as well. So, this is really genius mathematicians are the ones who came up with that floating point. Yeah.
Is it a little bigger with a double?
Yeah, they the sign bit's still the same, and then it's just that the exponent and fraction are bigger. I believe the exponent is 16, and the fraction is now. I gotta do the math in my head.
So it's different.
Yeah, it's different. Yeah. The formula is still the same, I believe. Yeah, the formula is still the same, but just basically you have more digits in the exponent and fraction now that you can have. So I can get smaller decimal numbers, fraction numbers, sorry. Right. Hopefully you all know that computers only know numbers, right? So we want to use characters or letters in a language,